Good afternoon, everyone. I welcome you all to the seminar series of Mathematics and Physics Department. I'm excited to announce today's speaker, Andrew Binder, who is currently a research assistant at Brookhaven National Laboratory and the Research Foundation at Stony Brook University. He received his bachelor's in physics and applied mathematics from UC Berkeley in 2024, followed by a master's in quantum information science and technology at Stony Brook University in 2025. While at Berkeley, he worked on quantum control software at the Advanced Quantum Testbed in Lawrence Berkeley National Laboratory under Professor Irfan Siddiqui. Since then, he has pivoted to more applied physics research and is currently working under Professor Adam Figura on the Long Island Quantum Internet Project, where he is involved in two projects, building a free space entanglement source and assisting with the construction of a single photon quantum non-demolition experiment involving quantum memories. Outside of official research, he has enjoyed learning more about ion trap quantum computing and is excited to talk a bit about Qudits today. So over to you, Andrew.
Thanks for having me again, and thanks for coming through the snow and the cold. Appreciate it. So yeah, today we'll talk a bit about qubits, which hope to be a nice extension for higher dimensional quantum computing. So I guess just brief rundown of what we want to do today. So we're going to talk a bit about qubits first, sort of understand what they are, why we want quantum computing in general, and see where they may fall a bit short, and where we may want to look to higher dimensions and talk about Qudits. And of course, beyond theory, we want to understand practical applications of these things being realized and see how we may see this implemented in the future. So yeah, high-level introduction, right? We're not going to get into too much nitty-gritty. We're kind of just touching on the high-level details of what this is and how it works. So let's start where all computing starts, with classical computation. So classically, our unit of information processing is a bit, right? A bit is a 1 or a 0, light on, light off, switch activated, switch inactive. So this is our fundamental unit of computation. We use it because it's easy to make, and we can perform all kinds of Boolean logic with it. Boolean logic just refers to any kind of logic where the outputs are true or false. So we can basically, all of our computers right now operate with Boolean logic, with basic logic gates, and they're all powered by bits. So physically, a bit is, in our computers, represented by either the presence or lack thereof of some kind of charge. So a transistor or a switch just helps you determine, are we letting charge in or are we not letting it in? So 1 or 0. Well, okay, it works. We have computers that work, right? This thing is functioning, right? So clearly classical computing and bits make sense to an extent, but they are limiting because we are sort of limited to classical computing and sort of classical physics. So if we want to simulate quantum mechanics, if we want to understand certain quantum phenomena, perhaps we may want to exploit quantum mechanics in our computers as well. So can we do better? Can we exploit quantum phenomena to enhance our computational capability? The answer is yes. And we do that first with qubits, right? So a quantum bit, qubit, very creative, I know. So very simply, it's just a two-state quantum mechanical system, right? So where a regular bit was just on or off, 1 or 0, a qubit refers to a quantum mechanical system that can take on one of two different states, whether that's spin up, spin down, certain energy levels in an atom. Just any quantum mechanical system that has at least two states, we can use that as a qubit. Now, you've probably heard, unlike with classical bits, qubits don't necessarily have to take on a definitive 0 or definitive 1 state, right? They can exist in what's called a superposition of those two states. And until we measure them, we can use them as such, right? So this vastly improves our computational ability because we can do what's sort of called parallel processing. So we don't have to live with only one definitive state when we perform certain quantum algorithms. But then as soon as we measure that qubit, then we have to read it out as either 0 or 1. The same way, you might not know whether or not a a coin will land heads or tails, but as soon as it lands, it will land either heads or tails. It won't land in some weird mix of heads and tails. So we use 0 and 1 representationally for our qubits, and this is what's called the computational basis. Not really super relevant, but an arbitrary state, like an arbitrary qubit state psi, is represented by some combination of 0 and 1, right? And it lives on what's called the Bloch sphere, which is a nice theoretical representation of these qubits. So quickly, before we move on with like physics, just a bit of math. So I'm going to use what's called Dirac notation to notate these qubit states. So instead of just writing the number 0 or the number 1 like we would do for just classical bits, we represent the states 0 and the state 1. So the state 0 would look like 1, 0, where alpha is 1, beta 0, and the state 1 is alpha 0, beta 1. So in essence, these quantum states are vectors, right? And so instead of having just a number represent our state, we now have a vector, which is really, really powerful. But just as with vectors, we can take their transpose, their conjugate transpose, what's called the adjoint. We can take inner products. We can take outer products. But the very important restriction we have is that our probability needs to be normalized, right? So the probability of measuring a state has to be 1, right? The probability can't be less than 1. The probability can't be more than 1. So that's why it's very important that we, for any arbitrary state, the probability of measuring something, whether it's 0 or 1, has to be 1. That's what that norm squared expression means. Now, there are different measurement bases that we can use in this type of computing. We can use the computational basis. We can use what's called the Hadamard basis, which is sort of a superposition of 0 and 1. There are a bunch of different bases, but for simplicity, we're going to really focus on the computational basis because it provides the best analog to classical 0 and 1 states. OK, so I mean, I just said that qubits are two-state quantum mechanical systems. That's nice, but like, what two-state quantum mechanical systems are we using to actually implement qubits? Well, there are a couple of like very popular options that we use. So the 4 main ones that we use are what are called superconducting qubits, trapped ion qubits, neutral atom qubits, and quantum dots. So superconducting qubits are basically just we use what are called Josephson junctions, and we use their energy levels as the qubits. So the biggest players in this game, Google, IBM, these are the ones that are using superconducting qubits. So we're pretty good at making them, and we can make a lot of them. And so they have their own promises when it comes to putting a lot of them on a quantum processor. The other really popular ones are trapped ions. They kind of sound like how they're described, right? You take an ion, you trap it, and you look at its stable energy states, and those are your qubits. So certain leading institutions in this field are using trapped ions as the basis for their qubits. Neutral atoms are another form where you take sort of the ground levels of a certain Rydberg atom, and you take those as your qubit states. Companies like Quantinuum use neutral atoms, and then other research groups also like dabbling with these. And finally, you have quantum dots, which use electron spin, right? Spin up, spin down, those are your qubits. Great. I'm going to focus a little bit more on trapped ion qubits because they're cool. But these could work with other types of qubit implementations. But fundamentally, with a trapped ion qubit, you trap an ion, and you look at its stable energy levels. And those 2 stable energy levels are your qubits. Now, there are 2 popular options for which stable energy levels you can choose. You can choose what are called the ground state hyperfine levels. Those are called hyperfine qubits. So this is due to hyperfine splitting in the atom. Or you can take optical qubits, which are just the ground and excited states. So this image is a little baked, unfortunately, but these are this is an energy level diagram for the lowest states for a calcium ion. Calcium 40 is a very, very popular ion to use as the basis for trapped ion qubits. So you have your, yes, these are your S level, and then these are your split levels. Perfect. Well, OK. If you'd like to see a cleaner image like this, come to me afterwards, and I will show you the slide where the image is not baked. Yeah. Okay, so qubits are nice. Qubits work. We have computers with qubits, right? IBM's already been doing stuff. Google's already been doing stuff. So do we bother going bigger? Like, what's wrong with qubits, for lack of a better question? Well, scalability. That's the big thing we want to focus on. So the computers that we're building right now are not exhibiting the quantum advantage that we really want to see from quantum computing, right? And this is due to a couple of issues. Issue one, certain quantum algorithms we run just require a lot of qubits to work, right? So if you even want to execute any kind of quantum algorithm, you just need a lot of qubits. Another issue is quantum states are really prone to errors, right? Quantum systems just in general are already kind of unstable and finicky and prone to a lot of just random errors that completely destroy any information that you might want to glean from the system. Which means, just like in classical computers where we have error correcting schemes, we have redundant bits, we have all that in case you scratch your hard drive and you don't want to get everything corrupted. We have quantum error correction protocols that also require a lot of overhead. So for superconducting qubits, for example, that requires on the order of like 1 million qubits, right? So we need a processor with 1 million qubits if we want to be able to meaningfully perform quantum error correction and achieve like quantum advantage through those processors. For other qubit schemes, the overhead required is lower, but it's still far more than what we currently have. So we have a couple of options then. Either we can try to get better and better and better at making qubits so that eventually we can just put a bunch of them on a processor and say, all right, we got it. We've finally figured out how to do it. We can maybe try to come up with better error correcting protocols that require less overhead to try to solve that problem. Or maybe we can look to higher dimensional qubit states, or Qudit states, as we'll talk about in a second. So maybe if we increase the dimensionality of our space, then we might have an easier time actually performing computations with fewer units of information. So, as it turns out, we can do better than qubits in terms of that. So we come to Qudits. The D in the middle stands for the dimension. So with a D of 2, you have a qubit. With a D of 3, you have Qudits. Yes, Qquarts, whatever. We have funny names for the other options. So now, instead of taking a two-state quantum mechanical system, we take an arbitrary amount of levels in our system. And then however many levels we're interested in, that is our Qudit. And that will determine the dimension D that we have for our Qudit. And as it turns out, that actually makes more sense even physically, because a lot of these systems that we use for qubits already have more than 2 distinct levels, right? You can split further into the atomic energy schemes. You can have Zeeman splitting. You can have other types of splitting, right? So we already are not necessarily restricted to only 2 levels within most of the quantum mechanical systems that we're even dealing with. So why don't we exploit them instead of trying to hide them, right? So now our arbitrary quantum state, instead of being a 2-dimensional vector, is a d-dimensional vector. And our basis states are 0, 1, 2, all the way to d minus 1, because we zero index when we count in computer science. So the question is then, OK, cool. So we can, in principle, think of these quantum mechanical systems as having more than just 2 states in a lot of cases. So how do we implement them? Well, with regular qubits, just 2-dimensional, what we did was we tried to excite from the ground state to the excited state. And that was the way we flipped between those qubits. So now, instead, we can just exploit the higher energy levels in the system with different laser frequencies, right? So instead of just having the one particular laser frequency that induces the first transition from the ground state to the excited state, we have different frequencies that induce the different transitions between these other states that help make up our Qudit, right? So this, for example, for a trapped ion, shows some of the different energy levels that we can exploit and the different frequencies of laser that we can use to excite our atom to those different levels to accomplish and achieve these various Qudit states. So even what we thought was already simple has deeper physical nuance, and we can exploit that deeper nuance with increased computational complexity. So okay, I sort of have been saying that, oh yeah, qubits have higher dimension, therefore, they can be used for easier computation. I mean, I just said that. So is there an actual application to using qudits instead of qubits for certain applications? Well, I really don't love that the images become so baked, but all right, I'll try to point at the different things. But the idea is, okay, why don't we try to simulate gauge theories, or specifically lattice gauge theories, with a qudit computer instead of a qubit computer? So very simply, a gauge theory is sort of an extension in quantum field theory where you hold the Lagrangian, which is sort of the main quantity that describes the dynamics of your system, you hold it invariant under certain types of transformations. And so these gauge theories then, as long as your Lagrangian is invariant under some of these gauge transformations, then you have some sort of description and set of equations that can describe some kind of system. So we can try to simulate these theories with a quantum computer because you can use quantum to simulate quantum. So there, if we have higher dimensional gauge fields, right, we want a state that has more levels than just 2 to describe these different fields. So this ought to be a simplified level scheme, but I mean, you can kind of see the different levels. But again, if anybody wants a better image, I can pull it up a bit later. But now the qudits are encoded in the Zeeman levels of the calcium-40 ions. This is research done at the University of Innsbruck in Austria. So Zeeman states are the levels that result from Zeeman splitting when you expose an atom to an external magnetic field. So in a lot of cases, actually, we kind of want to avoid additional energy level splitting in an atom, especially when we're working with qubits and only 2 states. We obviously don't want more states popping out. But in this case, when we have more levels than 2, we actually could exploit additional levels. And controlled laser pulses at these different angles and frequencies can then manipulate these qudit states. Okay, so qudits obviously have a bunch of these benefits that we discussed, but they also have certain challenges, of course, because if qudits were just objectively better with no drawbacks, we would have long abandoned qubits. So again, we have this higher available computational space, right? Because instead of being limited to 2-dimensional vectors and thus a 2-dimensional Hilbert space, or 2 to the n-dimensional Hilbert space if we have n qubits, we go up to d-dimensional vectors, and thus a d to the n-dimensional Hilbert space if we have n qubits in our system. So we have a higher computational space, which means we can use fewer qubits to simulate certain algorithms and error correction protocols. And since qubits are just a special case of qudits, right, we can still implement qubit circuits on qudit processors. But more states means we have slightly more difficult entanglement procedures between qudits. We need to precisely manipulate multi-state systems rather than just a 2-level system. And this gets hard. So there's still work that needs to be done to improve the fidelity of these qudit states and actually make them something that we can implement more large scale in a processor. But this work is already being done, and proofs of concepts are being demonstrated at Innsbruck, again, where they conducted an experiment on qudit entanglement with trapped ions. Because again, for a lot of your algorithms and error correction protocols, entangling 2 different qubits or qudits is extremely important. So what they did was they set up a slightly modified entanglement setup from the standard setups that we see on qubits, and they have this additional transformation that allows us to switch between certain energy levels. And so we can successfully, with qtrits and with some other dimensions, demonstrate entanglement. Now, of course, entanglement fidelity is never truly 100%, but the challenge is getting the fidelity really, really high. Because if your entanglement fidelity is low, you're not meaningfully gleaning information from that entangled state. So the fidelity that they demonstrated for up to 5 dimensions is pretty good, which means that we're on the right track. And it means that we could, in principle, use these in much more compact processors, right? Instead of having thousands and thousands and thousands of qubits on a processor, we can drastically reduce the overhead that we need if we instead take, like, I don't know, a 10-dimensional Qudit and use that as the basis of our processor. Okay, so that was a lot. But very, very sort of briefly summarizing what we did, we kind of talked about qubits, right? We talked about the fundamental basis of quantum computing and how we want to already extend from classical computation to quantum computation. And qubits already have a lot of promise, right, in this field. But they're only two-dimensional, which means that there's a lot of overhead still required. We still need to figure out how to fit a lot of them on a processor. So maybe it might be worth looking at higher dimensional units of information as the basis for our processors, right? Because life already is rarely only two states, right? There's already much more complexity in the systems that we've already been looking at. So why not exploit that complexity? Well, that's what Qudits aim to do. So there's, again, so much more work that we need to do to really, truly realize the potential of these units of information and to see them in actual processors. But it is the hope that perhaps, maybe, instead of qubit processors, we might see Qudit processors that can perform much more complicated algorithms with fewer units. So maybe this is what we need to really push quantum computing just that much further and realize it that much sooner. Thanks for coming.
Any questions?
Yes?
Yeah, I have a question. Like, based on what I heard from the IBM quantum computers, like, essentially they're blocking the amount of high energy levels that they're allowed to for a person to have. Like, right now it's only accessible for qubits, essentially. Do you have like any idea, like, how many dimensions or energy levels is like the limit? Like, is qubits like the limit where like we will actually see the benefit, or should we go like higher and higher?
So just to sort of recap the question, you're asking, like, is there a limit to how many levels in a system we can exploit?
Yeah.
So, I mean, the most accurate but least satisfying answer is I have no idea. But, like, in principle, for a lot of these systems, you got a lot of levels. So the amount of levels you can exploit, in principle, is kind of almost unlimited. But the question is there some sort of opportunity cost where, you know, if we try to deal with like a 100-state qubit like Qudit, is that going to work? So, excuse me, the research at Innsbruck demonstrated fidelity up to d equals 5. And to my knowledge, I don't think many research groups have done anything past like d equals 20, I think. And that might already be me making up a number. But like, that's sort of the feasible limit that we're currently working with. But if the question is, can we go further? Someone's got to try, right? And maybe we'll see a benefit.
Can you say a few words about how they demonstrated Qudits with up to 5? Actually, what they did, how they demonstrate?
Like, how did they create a higher dimensional?
Idea of the work.
So the idea is, instead of just using a single type of laser frequency to excite the ground state into a higher excited state for qubits, we use different laser frequencies to excite between different energy levels.
Different lasers or different laser frequencies with one laser?
So logically you could try to maybe use different lasers, but if you use one laser and then just a couple AOMs or EOMs within that laser, you can use the same laser but different frequencies for that one laser. So that dramatically decreases the overhead of even trying to come up with a single Qudit. If we needed a bunch of lasers, like a bunch of different lasers for a single Qudit, that might already be really challenging, especially to implement a lot of them on a single processor. So it is really nice that we can only use one laser but just different frequencies of that single laser to already initialize different Qudit states. But we still got a long way to go. Yeah?
You mentioned qubits being used to simulate lattice gauge theories. Is it that you need qubits to simulate them, or are they just more efficient than qubits?
So the question of whether or not you need something or don't need it is, I guess, kind of difficult to answer, because, I mean, maybe you can get away with, using only two-dimensional
Well, I mean,
states.
is it physically possible? That's what I mean.
Oh, whether it's physically possible to simulate higher dimensional gauge theories with like a qubit? I don't know enough to give you an answer. But it does make sense that if you have a higher dimensional field, you might want a higher dimensional base unit to make that. You could probably string together a sequence of qubits to make it the same way how like one 4-dimensional qubit can replace 2 qubits, right? So I'm sure you can sort of go the opposite way and try to, put a bunch of qubits together. But that already gets really, really complicated. So it would help, it would help dramatically if we can have higher dimensional states representing higher dimensional fields.
And just as a follow-up to that, so as far as I know, quantum advantage has been very difficult to demonstrate, even for qubits. So I'm curious, are there particular algorithms that demonstrate quantum advantage, for example, Qudits or other ones for pieces of information?
So quantum algorithms in general, a lot of them do exhibit quantum advantage, right? So for example, one of the most famous ones that we know is Shor's prime number factoring algorithm. It does factor in significantly faster time for larger primes, right? The problem isn't necessarily do the algorithms exhibit advantage. The question is, can we even implement them, right? Because if I say, oh yeah, you can do this thing, you need 4 arms to do it, right? Like, great, awesome, I don't have 4 arms, so I can't do it. So the challenge right now is creating a 4-armed person, right? Making a computer that has enough qubits for us to be able to execute the algorithm and correct any errors that might result in our qubit just existing. So that's been the big challenge. And hopefully with Qudits, because they are higher dimensional, we may require fewer of them in our protocols, and thus we can just make more of them a little bit more easily, since we won't need like thousands of them on a processor. Oh yeah, sorry, yes,
Yeah,
I'm blind.
Yeah, just a question, like essentially for qubits to like enter data for it, like you use an encode essentially from the rest state. Like, would there be more space available to insert more information to a qubit essentially?
Will there be more space?
Not space exactly, but like how like for quantum machine learning, like you have a certain amount of points that you can actually give information for the algorithm. Like, would there be like that higher dimension allow for a better interpretation of the information that you put in?
So I think if you keep that information the same, right? If you feed it this, like if you feed a higher dimensional qubit what you would be feeding a qubit, yeah, you do have like extra available information that you're not necessarily going to be using. But I think the big advantage when you have higher dimensions is you can just feed it different information, right? You have extra precision you can use, right? So instead of being limited to, oh, I can only ask it true-false questions, I can ask it a yes, a no, a somewhat agree, a somewhat disagree question. Like, all of these additional states are things you have available to you. So that's like a big thing that could potentially help us.
Any more questions?
Oh yeah?
Just kind of following up on what I previously said. This is more like a theoretical question, but so let's just take, for example, like one quantum algorithm, like Bernstein-Vazirano. So like
Sure.
a series of n qubits can discover a secret string, and I think there's quantum advantage for this or something like that. Are there algorithms that only work for qubits or onwards, but it would not work for a qubit? Does that make sense? That display quantum advantage, or is that still a theoretical problem?
So, okay, so I guess, okay, so your question is, are there algorithms that like don't present quantum advantage with a qubit system, but do present quantum advantage with a qubit system? I don't know. I don't know.
I think
Maybe?
it's not an open question, but
Whether or not it's an open question, I'm not sure. Maybe this is just a I don't know enough to give you an answer, but I'm sure like people are trying to figure that out. And if the answer does become yes, then the desire and the demand for qubits becomes just exponentially bigger. Yeah. But already the jump from classical bit to quantum bit, that's such a massive leap. Like that in and of itself is already the thing that you're gleaning the advantage from. But again, I can't speak to how much of a leap then going from a two-dimensional qubit to like a four-dimensional qubit would be. But I'm sure there is benefit to be gleaned from that. But the big thing when it comes to quantum algorithm advantage is going from classical to quantum. Like that's such a crazy leap. Yeah. One more? Yeah. Go for it.
Can you use like those higher dimensions to like prevent like errors in the qubit itself? Like.
So.
Yeah.
Yeah. Can you use those levels to prevent errors in the qubit?
Like the coherence and like any gate redundancy.
So. Can you use like extra levels as redundant states? I am not sure. I think the main challenge with quantum error correction is not necessarily redundancies, right? Because with classical error correction, like, okay, yeah, just throw a few redundant bits in there so that in the event that one of your things gets damaged, you still have that extra bit that's storing the same information. With quantum, you can't clone an arbitrary state, right? Because if we could clone an arbitrary state, great. Just clone it, you got a bunch of redundant states, and there's your error correction, nice and easy. But no cloning says, no, we're not gonna make it that easy for you. So I think the challenge with error correction is a little bit different, where you sort of, not necessarily exploiting individual levels within a qubit to store information, but having a bunch of them strung together, sort of correcting for flips. Whether or not an individual qubit state can do that just on its own, do not know. But if you have higher dimensional states, right, you require fewer of them strung together in some of these error correcting protocols. That is the big thing that we hope to like exploit in terms of error correction. Yeah. Mm-hmm. Thank you for all the questions, by the way. Like, this is not, like, thank you. This is really good.
Thank you very much, Andrew, for this wonderful talk. And thank you, everyone, for attending this event. I hope to see you in future seminars, too. Thank you once again. Yeah.
Yeah, thank you for coming.